Okay, hello AP Chemistry class. This is your evening assignment for Tuesday evening, September the 3rd. Good news for you is there's no assignment sheet to go with this. What we're going to do is just have a discussion on this. It's a lot of vocabulary, and we're going to reinforce it tomorrow as well as continue to work on your POGIL assignment, and we'll go from there. So let's get through this in about 30 minutes or so, 35 minutes. What is electrical force? By the way, you should be taking notes. We started taking notes in class today, and so go ahead and complete those. And I'll tell you things that I would like you to write down. So what is electrical force? Previously, we said that similar charges, like 2 electrons or 2 protons, repel each other, and different charges, like 1 proton and 1 electron, attract each other. These are referred to as Coulomb forces. And for the AP exam, they like you to use that phrase, that you understand that it's a positive negative attraction, or a positive repulsion, or negative repulsion that's causing two things to either be drawn together or pushed apart. So those are called Coulomb forces, named after a scientist. So first we're going to deal with a concept called Z number. We did this in class, so this is review. Again, you want to just take some notes. I want you to write down at least what a Z number is, and it's good to give this example of lithium. Don't try to crowd your notes too tightly together. Skip spaces in between lines, makes them more readable, and underline keywords. So lithium has an atomic number of 3. The atomic number is called the Z number. So that's a note you should take, or that you probably did today. Atomic number is called a Z number. So for lithium, for example, its atomic number is 3. So lithium has a Z number of 3. Now, what is a Z effective number? Effective Z number, or Z subscript EFF, Z effective, measures how much of the pull of the protons an electron feels. So the Z effective number is a simple formula. You take the Z number and you subtract the number of core electrons. So what are core electrons? Core electrons are any electrons that are closer to the nucleus than the electron that you're interested in. So if you look at lithium, it has that 1 valence electron, and that's the electron in the outer orbital. So the core electrons are the ones inside the valence orbital, and those would be those 2 electrons in the first orbital. So just to carry out this example for lithium, the Z effective is 3, which is the Z number, the number of protons, that's 3, minus 2, that's the number of core electrons, and that gives you an effective Z number of 1. And what that means is that that outside electron, that valence electron, doesn't feel the pull of 3 protons, because those protons, remember, are pulling in the electron. It only feels the effective pull of 1 proton. So it's feeling a much weaker pull to hold it to the atom than it might seem. What that means is, and we'll study this in the next few slides, is that electron can be easily removed from the lithium atom because it does not feel the pull of the protons very strongly. All right, so here I define core electrons on this slide. The core electrons are the electrons inside the valence orbital, and the orbitals inside the valence orbital. The core electrons are said to screen or shield. So write down those definitions. Some textbooks call it screening, some call it shielding, and it doesn't matter. They mean the same thing. So what they do is they screen or shield the valence electron from the pull of the protons in the nucleus. So you can see how those 2 inner electrons are kind of blocking the outer electron, the valence electron, from feeling the pull of those 3 protons down there. And that's called screening or shielding. All right, so let's just take another example. So silicon. Silicon has a Z number of 14 because it has 14 protons, so that's its atomic number. And it has 10 core electrons, 2 in the first orbital and 8 more in the second. That's a total of 10 that are inside of the valence orbital. So the Z effective for silicon is 14 minus 10 equals 4. So although silicon has 14 protons, each of its 4 valence electrons, that should be a 4, feels the pull of only 4 protons. So that means those 4 valence electrons are not held as tightly as you might think with 14 protons pulling in on them. So what's an isotope? So atoms have three components: protons, neutrons, and electrons. A particular element, such as lithium, has to have the same number of protons to be lithium. Lithium has to have three protons. If it doesn't, it's not lithium, it's some other element. So what if we change the number of neutrons? Can it have a different number of neutrons? The answer is yes, and that's called an isotope. So an isotope is an atom of the same element, but with different numbers of neutrons. Isotopes change the mass, that is the weight of the atom, but they don't change the charge on the atom. That's because neutrons don't have any electrical charge. So you see in both cases, these are two electrically neutral lithium atoms. They have three protons and three electrons, but the atom on the left is heavier than the one on the right. Okay, so we learned that a typical lithium has 4 neutrons, but occasionally we come across a lithium atom with only 3 neutrons. So that's the example we're looking at. So what's the notation for an isotope? You generally only use this if you're dealing with a situation where knowing the isotopes is important. But the notation is you put the atomic mass, or really the mass number of the particular isotope, on top. So the lithium with 4 neutrons is a 7 because there's 4 neutrons plus 3 protons gives you 7. The atomic number's got to be the same for lithium. It's got to be 3 or it's not lithium. The one on the right, it only has 3 neutrons, so it's 3 protons, 3 neutrons, gives it an atomic number of 6. So that's the way you write the notation. The atomic mass or atomic number actually goes on top, and the atomic mass or mass number, goes on top, and the atomic number goes on the bottom. So notice that the atomic mass or mass number is on the top and the atomic number is on the bottom. This is the opposite of your periodic table. Okay, so what's an ion? An ion of an element is an atom that has a different number of electrons than protons. So isotopes have different number of neutrons, ions have different numbers of electrons. And this is by far the most important of the terms that you're going to learn today, because most of chemistry deals with the relationship of ions to one another. So if you look at the lithium atom on the left, that's electrically neutral. It has 3 protons and 3 electrons. And if you look at the one on the right, it's lost an electron. And notice when you take away that electron, you also take away the second orbital. There's nothing in the second orbital, so you just don't include it. So the ionized lithium on the right has lost an electron. It has 3 protons and only 2 electrons. Therefore, it has a positive charge to it. Okay, what is a cation? A cation is an atom that has more protons than electrons. In other words, it's a type of ion. So this lithium atom is an example of a cation. It has a positive charge. So the little mnemonic we use is this. This dude is a positive cation. The smiling cat is positive. So he's a positive cation. So cations are positive. So what is an anion? Well, you can probably guess what that is. An anion is an atom that has more electrons than protons. So if you see this fluorine atom right here, you know it's fluorine because it has 9 protons, so it has to be fluorine. If you count the electrons, you have 10 electrons. There's one more electron than proton, and that means that it's a negatively charged ion. And we call a negatively charged ion an anion. So this fluorine atom is an example of an anion. It has one more electron than proton. An anion has a negative charge. So here's your little mnemonic for that. Your memory device is the grumpy guy is a negative ant. So negative ant, positive cat. Okay, what is ionization energy? Very important concept in chemistry. We'll talk about it a lot. Ionization energy is the amount of energy that is required to pull an electron away from its atom. So the man represents ionization energy. The protons are pulling in on that valence electron. The ionization energy must be greater than the energy the protons are pulling on in order to get that electron away. So the ionization energy must have greater pull on the electron than the protons. The energy the man with the rope must use to pull the electron away from the atom is the ionization energy. So let's look at the trends across the periodic table for ionization energy. So if you look at this, ionization energies increase as you go from left to right across the periodic table, and they also increase as you go from bottom to top. So what that means is the highest ionization energies are in the upper right-hand corner of the periodic table. So that would be elements such as helium, fluorine, neon, some of those in the upper right-hand corner. And there's a perspective diagram of it. So you can see the kind of the bars there. The highest one is helium. Those are the highest ionization energies up there. And the lowest are down in the lower left. That would be cesium, barium, rubidium, and some of the elements down in the lower left-hand corner. So ionization energy is greatest in the upper right-hand corner of the periodic table where helium is. Again, just draw yourself a little sketch of this and make that note. Okay, so let's reason why this is. Why do ionization energies go up as you go from left to right and go up as you go from bottom to top? So ionization energies are lowest when an electron is furthest away from the nucleus, has more orbitals. So let's look at bromine down there on the bottom right-hand side. You see how many orbitals bromine has? It has 4 orbitals. That means its valence electrons are 4 orbitals or 4 orbitals out from the nucleus, and it also means there's a lot of shielding core electrons. Look at all the electrons inside of the valence orbital. That means those outside electrons are being shielded from the protons of that atom. So what does that mean? They're not strongly attracted to the nucleus, therefore they can more easily be removed. If you look at fluorine up above, it only has 2 orbitals, and it has 7 electrons in its outer orbital, and they don't shield each other. They're side by side to each other. So since its electrons are much closer to the nucleus, it's harder to pull them away. So fewer orbitals means higher ionization energy. More orbitals means lower ionization energy. In other words, a lower energy is required to pull the electrons away. So that's down in the bottom left here where it says bromine has a lower ionization energy for its valence electrons than fluorine because it has more orbitals, so its valence electrons are farther from the nucleus. Now let's compare fluorine and lithium over there on the left. So lithium has a lower ionization energy for its electron. It only has 1 valence electron than fluorine because its valence electron is the same distance from the nucleus as fluorine's electrons. So they're both in the second orbital. Lithium's 1 valence electron and fluorine's 7 valence electrons are both in the second orbital. So fluorine's valence electrons don't get in each other's way. They don't screen each other because they're all on the same level. But lithium has only 3 protons to attract its 1 valence electron, whereas fluorine has 9 protons to attract its electrons. So fluorine is pulling on those second orbital electrons with a lot more force than lithium's 3 protons are. Therefore, fluorine has a higher ionization energy. It's harder to pull those electrons away from fluorine than lithium. So fluorine in the upper right-hand corner has a higher ionization energy than the elements below it or the elements to the left of it. Okay, what is electronegativity? Electronegativity is how much an atom wants to pull an electron toward it. So the man represents electronegativity. Electronegativity wants to pull in an outside electron. So let's compare the two. Ionization energy is how much an atom wants to hold on to its own electron. In other words, how much energy it takes to steal an electron away from that atom, to take one of its electrons, to have somebody else take its electron away. Electronegativity, on the other hand, is how much an atom wants to pull in somebody else's electron. At this time, we're not going to make a difference between electronegativity and electron affinity, but we'll get into those 2 terms later. We're just going to use the term electronegativity. Okay, So electronegativity, just like ionization energy, increases as you go from left to right across the periodic table and from bottom to top. So fluorine, oxygen, sulfur, chlorine, they have high electronegativities. Now, one thing you should notice is helium, neon, those noble gases on the far right-hand side, they're not there anymore. Why is that? Because they have full valence orbitals. They have 8 electrons in their valence orbital. So they're perfectly happy. That's why they're called noble gases. That valence orbital is like a crown, and that's their crown. They have a full orbital, a full valence orbital, and so they don't want to pull in any other electrons. So even though, yes, they do pull in electrons very strongly, they don't want any more electrons, and so you don't include them in electronegativity. And there's another perspective diagram. You see it looks very similar to the one for ionization energy because they increase in the same directions. And again, as I said on the last slide, you don't see the noble gases over there on the right. You don't see helium and neon and argon, krypton, the rest of them. All right. So electronegativities are highest when an electron is closest to the nucleus, has fewer orbitals. So again, it's almost a similar explanation to ionization energy. Notice that fluorine has fewer orbitals than bromine down below. Therefore, it's easier for fluorine to pull in an electron because it doesn't have all those shielding electrons outside of it. It only has 2 levels of shielding electrons that'll keep it from pulling in an outside electron. Whereas bromine has 4 levels of electrons that are kind of preventing its positive charge from reaching out and grabbing an outside electron. So fluorine has a higher electronegativity. It wants to pull in an extra electron a lot more than bromine does. Okay, now if we go in the other direction, lithium has a lower electronegativity than fluorine because it has the same number of orbitals but fewer protons. Okay, lithium has 3 protons and fluorine has 9 protons. So lithium doesn't pull electrons as well as fluorine. In fact, as you'll learn very soon, lithium doesn't pull in electrons at all, whereas fluorine does all the time. Okay, so what happens when low ionization energy gets together with high electronegativity? So what we're doing is we're putting a lithium atom together with a fluorine atom. So you have one atom, the one on the right, the fluorine, that likes to pull in, it has high electronegativity, it likes to pull in electrons, and you have lithium on the left that has low ionization energy, meaning it doesn't take a lot of energy to pull that valence electron away from lithium. So what do you think happens when they get together? Well, the lithium has low ionization energy, so it easily loses an electron. Fluorine has high electronegativity, so it easily gains an electron or pulls in electrons. So the answer is lithium loses an electron to fluorine. Okay, and there it goes. And it slides over there. Okay, so lithium has just lost an electron, fluorine has just gained the electron, and this is an important principle of chemical bonding that we're going to talk about this week. All right, atomic radius. So atomic radius, our definition of atomic radius will be the distance from the center of the nucleus to the outermost electron. In other words, it's like the radius of a circle. There's a more technical definition we'll get to later on of what atomic radius is. But even when we get to that definition, you can just think of it as just like the radius of a circle. It's the distance between the center of the nucleus, and the outermost electron. So the atomic radius is basically the size of an atom. It's how big the atom is. That's important in chemistry because sometimes atoms simply have to fit in between other atoms, and whether they can do that or not depends on their size. Okay, so atomic radius decreases as you go up the periodic table and to the right. So it looks like these are the same arrows that you saw before, but notice they're different. This one, the atomic radius is getting smaller as you go from left to right. Okay, so in the second row, for example, from lithium across to neon, it's getting smaller as you go from left to right, and it decreases as you go up from bottom to top. So why does that happen? Well, let's start with the bottom to top. That one's kind of obvious why the atomic radius would get less, is because you have fewer orbitals. So bromine has a larger atomic radius than fluorine because it has 4 orbitals compared to only 2 for fluorine. So therefore, fluorine has a smaller atomic radius than bromine. The one that's counterintuitive, that goes against what you might think, is this one, and this is one they're likely to ask you on the AP exam. Lithium has a larger atomic radius than fluorine. Now think about that. As you go from left to right across the periodic table, you're adding protons, neutrons, and electrons, going from lithium to beryllium to boron to carbon to nitrogen over to fluorine. You're adding, usually when you add parts to something, it gets bigger, right? But in this case, you're adding protons, neutrons, and electrons to atoms, and they're getting smaller. So why is that? Well, lithium has a larger atomic radius than fluorine because it has the same number of orbitals but fewer protons. So lithium doesn't pull electrons in as well as fluorine. So think about this. Lithium has only 3 protons to pull in its valence electron. Yeah, granted, it only has 1 valence electron, but it's the same distance away as fluorine's 7 valence electrons. And fluorine's valence electrons don't block each other. They don't shield each other because they're side by side. So if you keep adding, if you know you have 2 orbitals going across from left to right on the second row, you know you have 2 orbitals, and you keep adding electrons to that second orbital, but they're not shielding each other, and you keep adding protons to the nucleus, the protons are going to pull on that valence orbital and pull it in tighter and tighter and tighter, and it's going to get closer and closer. So lithium, because it doesn't pull on its valence orbital as much as fluorine does, is bigger. And fluorine, because it has 9 protons and pulls much more on its valence orbital and valence electrons, it pulls them tighter. So as strange as it may seem, even though you're adding protons, neutrons, electrons as you go from left to right, the atoms actually become smaller. So learn that point, understand that point, be able to explain that, because there's a good chance they will ask you that on the periodic table, because it doesn't seem to make sense, but that's how it works. Okay, so here's just a summary of all of them. So as we move to the upper right-hand side of the periodic table, ionization energy and electronegativity increase while atomic radius decreases. So just remember, ionization energy and electronegativity do the same thing. They behave in the same way. They go up from left to right, but atomic radius gets smaller as you go from left to right. And as you go from bottom to top, the ionization energy and the electronegativity increases, but the atomic radius decreases. So atomic radius works the opposite way as the other two. Okay, this is a plot. So look at this. Whenever you see a graph like this, kind of look at the axes and see what it's measuring. So it's measuring on the x-axis, or the bottom axis, the horizontal axis, the atomic number. In other words, it's each atom as you get bigger and bigger and bigger going down the periodic table from number 1 all the way down to number 92. As you're going up, it's a distance, and PM stands for picometers. It's 1/1 trillionth of a meter. So it's telling you what the atomic radius is, how big that atom is in terms of picometers. So if we look at it, let's go on up to the yellow, and you see that the yellow dot at the top, that represents lithium. As you go to the next yellow dot, that represents beryllium. The next one down represents boron. So you're going from left to right across the second row of the periodic table. And you can see that the distance, the atomic radius in picometers, is getting smaller and smaller and smaller. So those atoms are getting smaller. Then you get to neon at the very end. That's the very bottom yellow dot. And then you're going to go to the next row, which is sodium. And all of a sudden you jump up in atomic radius. Why is that? Because you added another orbital. So it got a lot bigger because you added that third orbital for sodium. But the same thing happens in the third row. As you go from left to right, you're adding protons. They're pulling more tightly on that third orbital. So those electrons, no matter how many there are in that third orbital, get pulled tighter and tighter and tighter. And so you can see the atomic radius gets smaller and smaller, and that happens for all the other rows as well. Okay, so as you go across the go across a period, a row, more protons are added to the nucleus. So this is the explanation for atomic radius, are added to the nucleus. The electrons are pulled in with greater force in the valence orbital, in all the orbitals, but in the valence orbital. This means the atomic radius becomes smaller. The energy required to pull an electron out, ionization energy, becomes greater because those electrons are being pulled closer to their nucleus. And the ability to pull in an electron, electronegativity, also becomes greater. That explanation is not quite as obvious, but again, there's more pull from the nucleus because there's more protons. So again, memorize these trends. You're going to use them a lot throughout this course. As we go down the periodic table, more orbitals are added. This makes the atomic radius larger. You keep adding circles to the atom. And the outer electrons are farther from the nucleus. This increased distance makes the ionization energy and the electronegativity less. It's easier to pull those electrons away, and it's also harder to pull in electrons from the outside. And that takes care of our video. So we came in at about 26 minutes. All I'm asking you to do is take good notes on this. I will be checking notebooks. I just want to see the key terms are there. You should underline them, draw key diagrams. Don't try to shortcut this, because this is going to be your textbook 6 months from now, 7 months from now, as you go into the AP exam. You want to be sure you can access this information quickly, okay? So do the work now, and it will pay off in the end. So no worksheet with this. We'll talk about these concepts tomorrow, finish our POG, we'll do some other things, and that's it. So have a good evening, and I'll see you tomorrow.